thanks, Kasia, for this opportunity to present some of my thoughts and results of my research in Old Dongola and vicinity. So one more time, so greeting everyone. In my speech, I will be discussing these technological issues related to post-medieval and modern pottery assemblages from Dongola and its surrounding areas. And just to remind, the Old Dongola is located in Sudan on the right bank of the Nile, between third and fourth cataracts. So the recent excavations led by the URC Grand have focused on the transition between the Christian and Islamic communities in the city. However, my focus will be on the latest ceramic assemblages, like between 17th and 19th century CE, and modern pottery production. So for this presentation, I have acquired vessels from the ethnographical context from Al-Gaddar and Jabarona villages. So here they are on the map, the bottom and on the top. So I will start with the theory and then move on to the methodology to finally reach some interesting issues that results from a more technological approach to the analysis of the pottery assemblages. So the traditional classification of pottery assemblages is based on morphological and stylistic features, sometimes supported with the petrofabrics, and usually the type is the variation of those three. However, this form of classification ignores the social and cultural complexity of the craft itself. So the crafting is never done in a socio-cultural vacuum. A craftsman is involved in a series of interactions within his or her community and beyond, and those interactions influence their work. So the aim is to understand the mechanism of those interactions and, as a result, to catch slightly more human actions and decisions. So one of these mechanisms is the transfer of knowledge. So if we can agree with the statement of Valentin Roux that the techniques are the visible expression of cultural and social groups, then changes in the mode of knowledge transmission will reflect changes in societies. So thanks to the ethnographical research, we can understand how this model works. So an apprentice is learning by observation and practice, but except of learning the way of doing things, he or she acquires a mental framework from the teacher. So the learning requires a close and sustained relationship between teacher and apprentice. So this relationship makes it easier to preserve bodily and mental frames, and because they are deeply nested, they are hard to change. So the learning networks might be connected with the technological traditions and the social identities. However, the learning within communities of practice can lead to technological distortions. So the replication during the learning processes in ceramics is never perfect, resulting in common and unavoidable distortions. As a result, changes in material culture are inevitable, but they might have different dynamics. So according to Valentin Roux, one more time, these changes can be classified as a continuous and discontinuous. So the continuous changes occur in the regular sociocultural interactions with the intergenerational transfer of knowledge, while discontinuous changes occur when the transmission of knowledge has ceased, usually during the population replacement. It's important to identify the nature of changes in the ceramic material to better understand the dynamics of the past communities. However, focusing only on the methodology may be insufficient. So ethnographic examples indicate that a vessel of the same size, form, and function can be made using different techniques and methods. So since techniques are the visible expression of culture and social groups, it's essential to identify the changes and their character in the technology. So from a morphological perspective, it's not particularly challenging to identify contemporary similarities. Some forms are more common than others, while certain forms are falling into obscurity and can be only discovered through the curiosity of the researchers who leave them from the dusty backyards and middens. However, this does not change actually anything. The persistence of some forms may vary between communities. Although I will only present a few forms, they are not the focus of my presentation, actually. So, for instance, on the left, there is a contemporary baking plate here on in the firing place. And this baking plate is with burnished internal surface and the lamps on the top of the rim. So we can observe similar features and functions in the archaeological record. So on the right, we can see a baking plate from the 17th or 18th century. And that's also possessed the similar features and function. The difference is only that here the burnishing is like on the darker surface than here, and this tiny baking plate from Jabaruna it's smaller actually than those from the archaeological record. So the another example is an incense burner. It's called Mukhar, and it's also from Jabaruna. And this example was fashioned in 2021. And as you may notice, it was covered with a thin layer of the red paint. I know that the picture is maybe not in that quality, but the paint is more or less on the top. So on the left, you can see a variety of mukhars that were acquired during archaeological excavations at Old Dongola citadel. So like the flat bases or cylindrical necks are the features that can be easily spotted in both ethnographic and archaeological contexts. So moving to the last example, there is a mid-20th century vessel calling Kadik. And according to the informant, the purpose of this vessel was to store milk and then process it into butter, like salmon. And from the technological point of view, the upper part of the vessel was made of assembled elements like oils or slabs. They are here. And then they were burnished. These same features and morphology have been found in the late Makurian cooking pots from the monastery in Old Dongola. So if morphology or the external features of ceramic vessels are not enough for the proper recognition of the past sociocultural dynamics, so then how we can investigate them? So I propose to focus on methods that can help to understand the fashioning technique. So I will present a thick section method of mesoscopic analysis that can be used in both qualitative and quantitative approaches. So these approaches are interconnected and can provide us with data that supports each other. So the thick section method is the main method of the sample preparation and further analysis. The goal is to find a practical solution for a theoretical problem. So in theory, the only diagnostical feature observed in every shard is the orientation of voids and NPI. So NPI is like non-plastic inclusions. So to achieve this, I select the sample and use a saw with a diamond blade to cut a shard into thick, like 1 centimeter sections. So after the polishing, I scan those samples on a regular flat scanner with the high DPI, and I usually prepare 2 scans, one with 2400 DPI and the second one in 600 DPI. And the latter one is used for mapping the NPIs with a stereoscopic microscope. So the mapping is kind of attempt to register all categories of NPIs in sections, mostly like the mineral temper, based on the Mohs scale. So this is because with this method, it's quite difficult to recognize the type of the rock grain. So by thick sectioning, we can acquire a detailed description of the fabric with all variation along the profile. So this data can be processed by a model analysis and granulometry. So finally, by using J-microvision software and the statistical analysis, we can acquire a distribution and orientation of all registered components. So, and the picture on the right is the result of scanning. That's how it looks like, you know, after cutting and then scanning. So to conduct a model analysis and granulometry, I divide the whole profile into 1 centimeter, like kind of boxes or belts. So in this case, we have like 15 boxes. Like as I said, each of them is like 1 centimeter thick. And this allows me to trace distortions or changes between certain parts of the vessels. So all data has been acquired through the microvision software, which is dedicated to the thin section slides, actually. So every single void or NPI is then registered either by hand or semi-automatically. And at the end, the complete data about the components such as size, position, elongation, etc., is available for the statistical analysis. So In the calculation, I focus on the main components, which includes matrix, voids, and various kinds of NPIs. So I describe the matrix only in two variables, like the oxidation pattern and major colors. However, for the voids and NPIs, I calculate like amount and the surface coverage, shape, whether a given component is more elongated or equant, compactness, so how close they are to the ideal circle, modality, and orientation. And this orientation is calculated according to the point 0, which is in the upper left corner of the profile. So these calculations led me to create some kind of surface coverage profile, so which mathematically reflect the compositional differences among the analytical boxes, those SQ, which are on the left side, on the right side, and within the profile. So this graph allows us to easily spot the compositional differences, such as the ratio between voids and grogs in the top of the vessel being radically different than that in the middle of the profile. So actually, this graph is just, as I said, is the mathematically result of what's actually going on in the profile of this vessel on the right. So the amount of data may help us to understand the nature of the clay paste itself. So in this example, the coefficient of variation between voids, grog, and quartzite grains is a very similar level. So the low differentiation may lead us to the conclusion that the clay paste is quite homogeneous and it has been prepared with care. So the craftsman create a vessel with similar physical properties along the preserved profile. So this could suggest that the intended function of the vessel was to operate in a utilitarian environment with a low thermal or mechanical pressure. So, however, this interpretation actually required more data. So, in the qualitative approach to analyzing vessels involves the observing of the changes in voids and NPIs. So the orientation patterns that appear in the vessel profile can be seen as a spatial tendencies in the orientation of components. The cluster of components with a similar orientation may result from a similar technical actions. So differences in porosity are also taken into consideration for this same reason. So analyzing the orientation of voids and NPIs in the vessel profiles is usually the only way to understand the fashioning techniques. However, these techniques are not often visible in scientific research and papers due to the lack of the sufficient methodology and the state of preservation of the vessels. So like the handmade vessels are particularly vulnerable to post-depositional processes, accidents, user traces, and inappropriate cleaning methods, and it's making it difficult to identify the technological traces. So on the left side, there is a vessel, it's external surface of the vessel, the cooking pot covered with a thick layer of charred food remains, and the upper part of the vessel, and with a highly burned surface in the lower part of the belly. The technological traces at the internal surface are easier to spot, but they are also quite eroded and this harder to interpret. So, like for example, those yellow U-shapes here are some sort of remains of the fingers of the craftsman. So the subsequent stages of fashioning vessel, such as finishing, surface treatment, decorative techniques are are easier to identify and interpret, even if the surface has been eroded. So it would be difficult to interpret this case properly. It is the same vessel actually, yeah. Like here we have like the internal surface of the vessel, and here is the profile of this cooking pot. So it would be difficult to interpret this case properly without the thick sectioning and mesoscopic analysis, just like the other similar examples, to be honest. So what can be observed here? So first, the upper part of the vessel had a significant and easy to interpret technological traces. So just this interpretation. The rim was created from a single coil attached to the clay slab from which the neck was made. The slab is approximately like 5 centimeters long. By the slab, I mean like this part between those, between here and here. And as there were no signs of the net distortion, I decided to exclude the other coils. So that's why I'm interpreting this part of the vessel as made of slab. So the lower part of the vessel had a completely different void orientation pattern, which are elongated, linear, and parallel to the surfaces. So one more time, I'm showing the profile. As you may see here, you have the voids in the profile, and the interpretation looks more like this. So there is a difference. So what is even more interesting is that the pattern comes to an end at the quite rapidly at the point of the largest diameter of the belly. So yeah, somewhere here. So in my opinion, the lower part of the vessel was made using the pinching and hollowing technique from a single lump of the clay or in a concave mold. And the latter seems to be even quite more probable because of the ethnographical analogies. Some of the fashioning techniques are easier to identify by the NPI's orientation, and this is the true for the vessel being presented. So in the center, there is a profile of a closed bowl with burnished surfaces and a red engobe covering, and it's difficult to determine what is happening in the upper part, but in the middle and the lower parts, there are the remnants of at least 2 coil joining procedure. So the middle part of the vessel appears to have been made using the S technique or alternate bevel joints. That's how it looks in the experimental example. So while the lower part of was made using the U technique, and it looks like this more or less. So as the consecutive coils, they are attaching to each other and make some sort of U-shaped joining. They are here more or less. So differences in joining techniques may indicate the different fashioning stages. So unfortunately, the lower part of the vessel is missing. So the presented qualitative analysis method allows for a better understanding of vessel forming techniques. So the erosion of the vessel surface is not a problem in the fixed section method actually. So, however, can we also analyze the macroscopically distinguished fabrics? So within a quantitative approach, I would like to focus on a few aspects. So first, how do macroscopically distinguished fabrics refer to morpho-functional classes? So are they any regularities? So how diverse are they and how to measure the diversity of the assemblage? And secondly, can we divide fabrics according to other technological features? So, and can we group them into wider entities? So if so, what does it tell us about the technological choices of potters? Does it correlate with the previous analysis somehow? Oh. No, yeah, there is a lot of numbers. So the following graph displays the displays the distribution of various fabrics within the morpho-functional classes in the form of a heat map, and the color coding indicates the percentage of fabric presented in the particular class. So a warmer color indicates a higher percentage. 5 of the morpho-functional classes are highlighted in green, indicating that they had fewer examples and could have a higher degree of error. So it has been assumed that less than 10 examples of the given fabric would not be the subject of the statistical analysis. So if you take a closer look on the columns, we can see that both cooking pots and jars were the most common used vessels, and they were made out of the more than 20 fabrics. So for example, both were made out of 21 different fabrics. When we consider the rows, the fabrics F1 and F2 appear in almost every morpho-functional class. However, can we spot any specific tendencies? So it seems that within the assemblage of F14 shirts, baking plates were quite common, while among F26 specimens, bottles had a higher percentage. Both were most commonly made out of F1 and F30 fabrics, and jars were mostly abundant in the assemblages consist of F3 fabrics. This graph can help us to easily identify some correlation between fabrics and the function of the vessel. However, the diversity of the assemblage may affect interpretation. the important point to note is that certain fabrics were used in more than one morphofunctional class, raising the question of whether they were more specialized or multifunctional. So I used the coefficient of variation and the Simpson reciprocal index to estimate the diversity of the assemblage. So the results were quite similar. The lower diversity of the assemblage indicated the higher specialization, and they were colored in reddish colors. Blue values match with the higher diversity and more multifunctionality of fabrics. So after finishing the calculation, I was left wondering what the results mean, actually. So I decided to exclude fabric F8 and F20 for my analysis, as they were too few. F8 has only like 3 examples, and 2 of them were used to the baking plate. So both coefficient of variation and Simpson reciprocal index indicate that those fabrics were more specialized, but it's not that simple. So next, I focused on the lifespan of the fabrics and found some surprising results. So like the late Makurian wheel-made fabrics have the highest value of diversity, which indicate that they were more multifunctional. However, there was one exception with the wheel-made fabrics like F26, and it was specialized and used in 84% of all 26 fabrics for making bottles, so including almost contemporary Jabana. So the second surprise was the fabric F1, which was the most abundant in the assemblage and used in virtually every morphofunctional classic. Nevertheless, both CV and SRI indicate some degree of specialization. So here's the fabric 1, and it seems that it looks the fabrics for more specialized purposes. But okay, so let's revisit the question posted earlier. Can we classify fabrics based on the technological features? So my answer is yes. And as I mentioned it earlier, I used the mesoscopic fixed section method of sample preparation and a range of analytical tools to determine the percentage of main components in each fabric. So the main components include the matrix, voids, and the NPIs, like generally speaking. And I have presented the result in the table on the left. So here we have the fabrics and matrix, voids, and NPIs by percentage in every specimen here. So on the closer inspection, we can identify some similarities between the fabrics. So based on the ratio between the components, I have to conduct a cluster analysis and group the 23 fabrics into 7 clusters. The clusters are shown on the graph with the axis Y, X, and Z, and the details of each cluster are presented in the table on the right. So it's worth noting that the fabrics in the same cluster may appear drastically different from a macroscopic perspective. The purpose of this grouping is not to classify them based on their appearance, but rather on their technical properties. Okay, so the following table displays the percentage distribution of morphofunctional classic among the clusters in the form of a heat map. So, like, it's similar to the previous graph, and it's not surprised that the jars and bowls are most popular items across all clusters. However, there seems to be an interesting trend emerging with the cluster 5. So in my previous analysis, I used the coefficient of variation to identify specialized and multifunctional clusters. So a higher CV indicate the more specialized fabrics with the class. Cluster 5 contains a highly specialized fabrics that is commonly used in cooking vessels, with 81% of these vessels used for cooking preparation activities such as baking and cooking. So, however, not all cooking pots or baking plates are made with these fabrics, since we observed like 19 out of 23 fabrics were used for the making cooking pots and 12 fabrics for making plates, as shown in the previous slides. On the other hand, the fabric 3 in the cluster 1 was quite common with the cooking pots, and fabric 6 from the cluster 3 was popular in the baking plates. However, both fabrics from the cluster 5 have unique physical properties like height resistance and the heat capacity, and both fabrics are using the steatite as a temper. So On the opposite side, there are two clusters, 6 and 4, which have the lowest CV. These clusters have been used for different classes of the vessels, but there is no clear sign of dominance within them. So, moreover, these fabrics have been used for both handmade and wheel-made vessels, indicating that they were less specialized and assigned to a broader class range. So Kasia Delelis-Danes argues that there has been an increase in multifunctionality within the post-Makurian pottery assemblage, and I agree with that. However, I'm trying to develop to delve deeper into these pictures. There are certain fabrics that are more flexible from a technological standpoint and can be used in a wider range of vessels. These are truly multifunctional fabrics. On the other hand, we encounter with more specialized fabrics with particular physical properties. And these fabrics require a certain level of knowledge and are linked to the intended function of the vessel. So I have presented some methods and approaches that can help us to understand the past social dynamics through the technological studies. So the conclusion led us to perceive the local pottery production as a result of technological choices and constraints, which are deeply embedded in the social relations. This social dimension of technology is referring also to quite personal decisions made by the people from the past. However, can we identify any signs of knowledge transfer in the archaeological pottery assemblage? In other words, can we identify a purely human decision that were passed down through the generation? And I believe that to some extent we can. So I have been applying the Wilke-Wendrich concept of micro variation, which helps archaeologists to understand and trace the tradition and the transfer of knowledge between generations by locating production in a community of practice. And at first, I was skeptical, but I would like to share some of my results and interpretation with you and invite the discussion, actually. So, for my case study, I decided to examine the variations visible within the baking plates made of two unique fabrics, F14 and F25. Those were in the cluster number 5, those. And F25 is actually the variation of F14. So these fabrics contain a significant amount of NPI in the form of crushed gray soapstone, talc chloride schist grades, to be more specified. The table on the left side show that in this particular case, like 32.8% of rock grains were presented in the paste. However, the amount of these grains varies within the profile, and in other examples, soapstone may even exceed like 40%. There were no signs of fashioning techniques on the surface, so fixed sectioning will be necessary to reveal all the details. So briefly, the walls of the vessel were made of coils, as you may see here. And as you may remember, the joining is in the U technique. But in the bottom part, we can see traces of slightly different component orientation. It's here. Thus, the base was most likely made with the spiral coil or out of the circular slab. So although the last one is the less probable. So it appears that the technique of wall fashioning has remained largely unchanged over time based on the ethnographical analysis and my research. However, in this particular case, it's a bit challenging to identify the technique due to the differences in the distribution size and amount of NPIs. One thing that is clear is that there is a significantly smaller amount of a soapstone in a clay paste compared to the previous example. So although this vessel contains just a quarter of the previous amount of soapstone, so it's unlikely to be a coincidence. So the reduced amount of the soapstone results in the deterioration of desirable features such as heat capacity and heat resistance. So from the utilitarian perspective, this baking plate has little to common with the previous presented baking plate made of fabric F14, despite being the less physically robust. So despite the worst physical properties, potters still decide to add a few grains of a soapstone to the ceramic paste. the reason behind this decision is a bit more complex, and it might be divided into let's say, like the three hypotheses. So there is no soapstone quarries near the Old Dongola. So therefore, without establishing a trade connections, there will be no way to replenish the steatite resources. As a result, potters will have to use lesser amount of crushed rock in their vessel over time. So another thought is that the variation in the pottery fabrication are linked to the characters, to the changes in the transfer of knowledge. And it is possible that someone arrived, just hypothetically, someone arrived in Old Dongola and established their own community of practice. So over time, the newcomers between the old timers, I was calling, but the knowledge about the specific properties of the steatite began to disappear. So eventually, potters would add only a few grains of the steatite because my teacher did the same. So the last hypothesis is that there were a few pottery workshops within the different communities of practice. Therefore, the micro variation in the fabrics could be linked to the different recipes developed independently in the different communities. So regardless of which hypothesis is correct, the technology of a soapstone tempering ended in the 19th or early 20th century, or at least what archaeology can say. So interestingly, the knowledge about the unique properties of this fabric continues to exist even today. So during my ethnographic research, I conduct an interview with the oldest pottery lady in Jabaruna, and it's calling her like Madame SR. She's in the most noble among the other pottery ladies and has also taught most of the potters in Jabaruna. To gain a better understanding of her work, I took with me a shirt with 18th century baking plates with a soapstone used as a temper. The outcome of this idea helped me to understand that she had been using soapstone as a temper in the past. As she's over 70 years old, it came to be inferred that in the second half of the 20th century, there were workshops in the region of Old Dongola where potters used soapstone as a temper. Due to the lack of the soapstone quarries in the region, customers were responsible for supplying the tempering material. Madame SR confirmed that this material is soft and can be cut with a knife, and its properties are valuable. Finally, she kindly asked me if I could give her some shirts with this fabric so that she can reuse it as a temper. A slightly more difficult question is the beginning of using of these techniques. If the hypothesis about the relocation of a group of people from the region of Delgo, because I suppose that's the region where this technique making from Delgo to Old Dongola in the first half of the 17th century would be correct, then by the technological analysis and comparison of those two assemblages, we'll be able to detect the possible distortions. So those distortions or changes might tell us something more about the way in which the outsiders became the member of the regional technological tradition. Unfortunately, I do not have the comparative data from the region where the mentioned technology might come from. And because of the situation in Sudan, it might be even more difficult to get them. However, if there was no migration of producers, but a migration of customers, then searching for diversity with the wool fashioning techniques will be pointless. In this scenario, the local potters would use the same fashioning techniques, but they might have created a new ceramic based on a new demand. Two vessel profiles were presented, which showed that despite the appearance of a new tempering material, potters created the vessel with the same techniques. So it seems that we're also dealing with the coiling techniques here, and some slightly different technique was used to make the base of the vessel. So this evidence supports the hypothesis of a customer's migration. So Madame SR from the Jabaruna also supported this theory by stating that there was no soapstone in the vicinity of Old Dongola, and the customers provide the soapstone. So, according to Pataro and Furtholz, the term innovation refers to new practices that have a lasting impact on routines of technologies. And it seems that innovating practices are more common in societies with higher consumption and greater inequality. in contrast, societies with less consumption and greater equality, they are more egalitarian, tend to be less innovative. And this seems to have been the case for the post-medieval inhabitants of Dongola. So researchers conducted by colleagues from the Umma project has showed that there was a high degree of status unification among the houses at the citadel, with an exception being the House of the Mek, the local leader. So innovations also appear in the modern pottery, and increasing consumption seems to be the main driver. As you may see here, we have a like the pottery assemblage from Debba, and here we have like the beautiful decoration made of the bottom part of the Coca-Cola bottle. So the second thought, that the soapstone temperate pottery, for example, can be seen as an innovation resulting from an increase of consumption expressed in an increase in demand for a new vessel. So those singular innovations appear in the wider ocean of technological orthodoxy. And this may force us to perceive the post-medieval society of Old Dongola as a fluid entity with the various dynamics. So the technology is actually an astonishing subject, and there is no single method to recreate a full chain operatoire. That what I'm trying to do is to spot the traces of technological changes with this late post-medieval material, especially at the walls forming stage, to understand the past socio-cultural dynamics. So thanks for your attention.